This video is on inverse functions and takes a graphing approach. To begin, we did a warm-up in class, and since I'm recording this lesson after I've taught it live, I want to make sure that everyone gets the same material. So above the pink line, you should copy those notes. Keep in mind that the formal definition is written in blue, green, and red, but in parentheses following each definition is sort of what you're going to do informally, how you're going to apply these concepts. Then you should pause the video to copy and try this warm-up as well. I will scroll down so that you can see the final questions. And when you come back, you should check your work. So you should have tried the warm-up. And if you graph the ordered pairs from this table, remember that f of x is y. When you graph them, you'll see like the green graph here. This is going from the origin at 0, 0. It's hard to see both colors at once on my graph. The green graph is the way this would look from the original table, and this does make a function because it passes the vertical line test. The function is also one-to-one because you can see that if you drew a horizontal line anywhere on this graph, it would only touch the green function at one point, and that makes a function one-to-one. So it is possible to be a function and not be one-to-one. For instance, any parabola, and this is just an example, but any parabola is a function, passes the vertical line test. But of course, if I drew a horizontal line right there in the middle of the parabola, I would see that it touches it at 2 points, so it fails the horizontal line test. So a parabola is a good example of a function that is a function but is not a one-to-one function. Okay, so once we made a new table, this is the table for the inverse. All I did was what it said in the directions above in red, which was, let's see if I can scroll back up here, which was just to switch the x and the y. And so that's simply what you should do. And so instead of having my ordered pairs like 0, 0, 1, 1, 2, 4, 3, 9, they are now 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. And so what happened when I graphed those was that you got something like the red graph. And I hope that you can see that the red and the green are simply reflections of each other over this line, y equals x. And that's what I was looking for in number 6, although you may not have used the same word. Every function and its inverse will be a reflection over the line y equals x every time. Remember that the line y equals x is the collection of all the points that are the same. 1, 1, 2, 2, 3, 3, 4, 4, negative 5, negative 5, negative 10, negative 10. And so it's always that perfect diagonal line. A function and its inverse are always a reflection over that line. And so visually, you can always check if you've done the function and its inverse correctly. Let's look at some notation here. These are the same tables, so you don't necessarily have to copy them again unless you didn't copy them down the first time. This is the part that I'm focusing on here. This is important. This is the notation for the inverse. And you can see that it looks like it has sort of an exponent of -1, but that is not an exponent. There's nothing mathematically that you're going to do with that. It's simply notation that means the inverse of function f. And if it's typed, it's usually this fancy f. When you write it, you're just going to write it like that. Here's the thing, you need to memorize what this notation means because sometimes we're not going to say find the inverse of the function. Sometimes we're just going to say find this. And you need to know that that means to find the inverse because finding the inverse is a really simple thing to do. All you have to do is take the points and switch the x and y's. And so you end up with the x and y in the different position. Remember, the domain and the range change places. So down here, I'm talking about finding an algebraic formula. Now, of course, there's technically ways to do this, but this is a pretty simple pattern. Let's look at the original table, f of x. And I hope that you can see that to get from the x to the y, we're simply squaring the x. And so the original function is y equals x squared, or f of x equals x squared. And if you look at the inverse function, remember, if we have to start with the x to get to the y, well, this one would be the square root, wouldn't it? And I hope you understand that from what we've always done, squaring and square rooting are inverse functions. One undoes the other. We've always talked about them that way. We haven't thought of them as visually this reflection over the line y equals x. But if you go back and you look at your graph, if you could picture the rest of this parabola, I mean, we just didn't graph any negative values for x. And isn't that a reflection here? So we're going to be talking about limiting the domain because a square root function would not be a function if I reflected this dashed line part of the parabola, which is why we stuck to just doing the positive square root. We'll discuss that in the next video and in tomorrow's lesson. But for now, I just want you to draw some connections in your head about what you're looking at on the graph, how this notation is used, and the fact that inverse functions truly are inverses algebraically as well. In the next video, we'll go more into domain and range and how we can limit those so that we maintain a function or a one-to-one function and are able to find the inverses.